Okay, so start fresh here. Section 12.2, iterated integrals. So our goal simply is to try to compute a double integral exactly. You learned in section 12.1 how to approximate a double integral, but what if you wanted to find the exact value of a double integral? How would this work? And section 12.2 gives you an idea. Well, I mean, if we go right, I'm looking for it here. Yeah, there's a theorem called Fubini's theorem. Okay, Fubini's theorem. And this theorem says that if you have some rectangular region R, where x is between a and b, and y is between c and d, then the double integral, okay, the double integral can be computed equivalently by computing a double integral where you do dy dx or dx dy. In other words, you can switch the order of integration. That's what Fubini's theorem is. Okay, that's what the theorem says. But I want to give you a little. I want to just give you a little feel for, well, how did they, how did they get that? What's that mean there in Fubini's theorem when they say when you have dy dx, dx dy? So I'd like to show you how they developed that idea. Let me see here. There's a, yeah. So in figure one here, I don't want that. Hold on. In figure one, you see a surface. You see a surface, and it's over some rectangular region in the xy plane, and there's a volume below the surface. And you see when they have that value of x there, how they draw in red a cross-sectional area A of x. All right, do you notice that in figure one? Let me ask you this. So in figure one, below the surface, okay, so like when, for the value of x on the x-axis, some value of x on the x-axis, if you think about the surface, if you were to cut the surface along that, like cut the surface along the plane, well, I want to be careful how I phrase it. Let me ask you this. Do you agree for different values of x that the cross-sectional area will differ underneath the surface? So they've drawn in there in figure one a red cross-sectional area. Ian agrees. And that red cross-sectional area will differ for different values of x. That's why you have the a of x there. Now, in calculus 2, if you remember from chapter 6, okay, if we wanted to find the volume of that solid, the volume would be the integral from a to b of the cross-sectional area a of x dx. Okay, that's something that we teach here in calculus 2 in the Stewart text in chapter 6. So again, if I go back to the picture, how many remember in calculus 2 finding volumes of solids? It's something you should have seen. And when they talked about finding volumes of solids, yes, well, yeah, like a discs and so forth. And one of the things they talked about, they like if you want to find the volume underneath this solid in Figure 1, and notice the limits on X go from A to B. If you wanted to find the volume of that solid, okay, the volume of that solid would be found by taking the integral from A to B of A of X dx. Okay, that's the volume. That's a formula for finding volume as well as a double integral. Okay. The volume of the solid S that lies above region R and under the surface, f of xy. But this area, A of X, this cross-sectional area, okay, this cross-sectional area, well, A of X, based on the picture, is equal to the area under the curve f of xy from C to D. If I go back to the figure here, back to Figure 1, isn't that area A of X equal to the area underneath the curve C? And the curve C goes from, the limits on the curve C go from C to D. Can't that cross-sectional area, that red cross-sectional area in Figure 1, be thought of as a single integral with respect to y? Okay. Where your limits are from C to D and your function is f of xy. F of xy is a function that defines the surface, but if you keep x fixed, that cross-sectional area A of X will be the integral of the function of x and y with respect to y going from limits C and D, going from limits C to D. That's what they're saying right here. And so you see, it's actually a very beautiful development of the double integral formula. We can actually take that area there and substitute it in the volume formula above. And if we do, we get an expression for the double integral. We get an expression for the double integral. And it turns out that since we have constant limits, A, B, C, and D, we can actually switch the order of integration. You might need to take a look at this a little bit, but it's just sort of an intuitive, I feel, it gives you an intuitive feel on how on how to compute a double integral. And in fact, it turns out that the double integral, if you have constant limits, A, B, C, D, you can switch the order of integration and get the same value. That's by Fubini's theorem. So I'll tell you what. Let's go ahead and look at some examples here. Let's look at some examples. I think you'll need to. I mean, are there any questions about how they come about this double integral? Basically, let me just see if I can highlight. Hold on here. Yeah. So what I've done is based on the hold on here. This isn't. Is this? No, no, no. This is what I want. Hold on. I just want to highlight these three formulas. I'm getting better at this. You got to move the. Well, all right. So really, a double integral is based on going from the first formula there, the volume formula, to understanding that the cross-sectional area is equal to the integral from c to d of f of xy dy, and then substituting that area in the volume formula above to get what's highlighted here. It makes sense because if you look at figure 1, that cross-sectional area is an area where x is fixed. You fix x, and the cross-sectional area is the same as a single integral from c to d. Those are the y limits. But then the function, you know, the function above is the function of x and y. That's why you're able to, the second highlighted yellow formula there, that's why that's true. That area function of x is true, the second highlighted formula. And if we substitute the integral in the second highlighted formula for the volume function in the first formula, we get the double integral. So is this a little helpful? Just to kind of see why it's true, an intuitive feel. Is maybe give me a thumbs up if this is intuitively a little bit helpful. And then we'll do a couple of examples. But okay, thank you, Juliana. Thank you, Ian. Thank you, Ellie. I just thought it would be helpful and good. I'm glad it is. So on that note, let's go ahead and get to some formal examples here. So mark this moment. This is your first double integral, everybody. First one you're going to do. Let me give you a moment to copy the example down. I like the sound of that. All right, so Ian's shaking with anticipation here. But this is a really, you know, this is like, how many remember the first, when you got your, like when you turned 21? Well, some of you maybe aren't 21 yet, but when you turned 18, although some of you might not be 18 yet, but you know what I mean. How many remember the moment when you got your driver's license? How many remember that moment? None of you? Wasn't that a big moment? Still attempting to get it. Okay, Gordon. All right. All right. Yeah. You got to get cones to learn how to park. Yeah, that's right. Well, let's go ahead and do this. Julia has her test this month. Good luck, Juliana. All right, excellent. All right, let's evaluate this double integral. First of all, what are the y limits? What are the y limits? What would they be from? Right, Ellie, 1 to 2. And the x limits are from 0 to 3. Let's see how to evaluate this. So we go to the next page. Now, the first thing I note is right here. This double integral means, okay, this double integral here that we are computing means we are finding the volume between the surface given by the function x squared y. We're finding the volume between the surface and the xy plane over the region D below. The x limits, right? The x limits go from 0 to 3. Okay, and the y limits go from 1 to 2. Now, I know you're copying, but let me ask you, do you think this, based on this function here, do you think the volume's going to be positive or negative? What are your thoughts on that? I mean, do you think the final answer should be positive or negative? What do you think? What is this? It should be positive. That's right, Charles. That's good, Juliana. Good, Madeline. This function is always positive in quadrant 1. So the volume between that function, x squared y, and the xy plane over region D, that volume would have to be a positive volume. Okay, let me give you a moment here. Okay, so now it's hard to do two things at once, right? When you learned about integration, you learned about integrating with respect to one variable at a time, and we're going to do this. So what this means, this integral, when you have the dy and the dx, it means you're integrating with respect to y first. That's number one, that comes first. And then you integrate with respect to x second. And you notice I have here brackets, or now WebAssign, incidentally, will not understand an answer that has these kind of symbols in it, unless it's like you're doing like a domain or something like, or a range or something like that. For WebAssign, always use parentheses for grouping symbols. Okay, just wanted to mention that. But okay, so I use these grouping symbols here, and I'm going to integrate with respect to y. Now, like when you learned about partial derivatives, and you had a function of x and y, and you did like the, if you did the partial derivative of f with respect to y, what variable was held constant? If you have a partial derivative of a function of x and y, and you're computing that partial derivative with respect to y, what variable is treated like a constant? X. In other words, that's right, Hunu. You're holding x constant, and you're looking at the rate of change of the function as y varies. Okay, for a particular, at a particular point, but you're holding x constant. Well, it's the same with integrals. You see, I'm integrating with respect to y here. I'm integrating with respect to y. And so that means I'm going to hold the x squared constant. And constants can be brought out in front of the integral. Okay. And you notice I still keep my grouping symbols here. So of course on your exams for the, you're doing your integrals, you're working them out, should be working them out by hand, and in the work I'll want to see that work. So now the integral of y dy is y squared over 2. The limits go from 1 to 2. And you end up then getting now, well, you have to evaluate this integral here. You have to evaluate this. So it's a calculus 1 problem, right? You just put in the 2 and the 1. There you go. And you'll get 3/2. And so you end up with the integral from 0 to 3 of 3/2 x squared dx. Okay, so are there any questions on this page? Okay. How many find these grouping symbols here helpful? These grouping symbols. How many find them helpful? Good. Madeline does. Wonderful. Good. Good. Well, we're ready to move to the next page then. Are there any questions before we go to the next page? All we have to do is evaluate this integral. May I go to the next page? Maybe give me a thumbs up when you're ready. All right. Okay. All right. Well then, here then we bring the 3/2 out in front. And the antiderivative of x squared is x cubed over 3. And we work it out, and we're going to get 27/2. That's going to be the value of our double integral. And incidentally, by Fubini's theorem, since all of our limits are constants, the 0, the 1, the 3, the 2, we have constant limits. So if we were to switch the order of integration and integrate with respect to x first instead of y, we would end up getting the same answer. You could try it for yourself and see. All right, let me give you a moment to copy this down, and please let me know if you have any questions. So indeed, the volume then is indeed a positive answer. And this is the exact volume. So volumes were important, you know, the idea of finding a volume, one of the motivations behind it, you know, back 300-400 years ago was that merchants wanted to be able to compute the volume of wine barrels. That was one of the, you know, one motivation. Now, actually, that can be done. You don't need calculus 3 to do that. But you know, finding volumes is actually very important in applications. So, are there any questions before we move on to the next example? All right, give me a thumbs up when you're ready to go to the next example, and we'll move forward. All right. Charles is good. Madeline's good. Ellie's good. Wonderful. Malik's good. Excellent. Thank you, Juliana and Marwan. They're good too. All right. Well, then let's move forward. Let's look at another example here. Okay. I'll give you a moment to copy this example down. Okay, so now here we have an interesting integral. Based on what the way the double integral has, I should say double integral, we have a double integral. Based on the way the double integral is written, are we integrating here with respect to y first or with respect to x first? That's right, Charles, with respect to y first. So, okay. Well, so of course, we want to iterate the integral. Okay, so iterate allows us to just, it helps us separate out the double integral. And we're going to integrate with respect to y first. So let's go to the next page. So again, I think it's always helpful to know, to be able to interpret what we're doing. We are finding the volume between this surface, y times the sine of xy, and the xy plane, okay, over the region D below. So this is the region D. The y limits go from 0 to pi, okay, and the x limits go from 1 to 2. So that's the region D. Now, when we do this problem, okay, I do my iteration, but in this inner integral, what variable, the integral with respect to y, the inner integral, what variable is being held constant, the x or the y? Well, that is exactly right, because that's right, Ian, because we're integrating with respect to y. If you were to take the partial derivative with respect to y, you would hold the x constant, right? It's the same with the integral. If you have an integral and your integrand has two variables in it, but you're integrating with respect to one of them, you hold the other variable constant. So I say here, well, we're going to need to use integration by parts to get the antiderivative of the inner integral. Now, why am I saying that? Well, I think of something like this. If I had the integral of y times the sine of 2y dy, okay? These are just, of course, parentheses. How many remember from like their calculus days doing integrals like you see there, the integral of y times the sine of 2y dy? How many remember in calculus 2 doing that? The reason I like the x is constant, right? So I think to myself, well, all right, if I had the integral of y times the sine of 2y dy, 2 is constant. So I mean, I'm just kind of thinking of an analogy back in calculus 2 when you learned integration by parts. So none of you recall like integrals like that? What I'm trying to say is this. What I'm trying to say is this. I'm looking here at this inner integral. And I say right away, oh, integration by parts is needed to get the antiderivative of that inner integral. Why would that be? Well, if you had an integral like the integral of y times the sine of 2 times y dy, okay, you know, you'd let u equal y, and dv would equal sine of 2y dy, and then you'd have du equals dy, and v equals the antiderivative of the sine, which is negative cosine of 2y, all divided by 2. And then you would do integration by parts. Okay, integration by parts is integral of u dv equals uv minus integral of v du. Does that help refresh your memories a little bit? Okay, good, good. So the only reason, I mean, you see this x here, this x with respect to the inner integral, it's a constant. So it's really no different than this integral here. Now, I could go forward and work it out. I could do this integral. I could do the integration by parts and work the integral out and get the answer. I actually did it just to see. But remember, we have constant limits here. All of our limits are y limits and our x limits are constant limits. So that means that we can try to switch the order of integration. Maybe we can avoid doing integration by parts if we switch the order of integration. So the double integral, where the order of integration is dy dx, would equal the double integral where the order of integration is dx dy. So I'm saying let's go ahead and try to integrate with respect to x first and then y and see if that's a little bit easier. You see what I'm saying? You see what I mean? It's not that I can't. Thank you, Ellie. Excellent. Excellent. It's not that I can't work the double integral out the first way here, where I integrate with respect to y first and then x. I can do that. It's just I want to see if maybe I can avoid the integration by parts. Now, you can't always avoid it, right? But let's see. So are there any questions before I go to the next page? Okay, well, I'll go to the next page then. So here now, okay, here, that's the next there. I'm integrating with respect to x first. And here's the antiderivative. Remember, the y is treated just like a constant. So I just, I mean, I could pull it out in front of the integral, but I could also just let it there. And the antiderivative of the sine is minus cosine. But then I have an x times y there, so I have to divide by y. It's no different than if you had, you know, if you had the you know, the integral of the sine of hold on here, the sine of 2x dx, right? The antiderivative of that would be minus cosine of 2x over 2, right? Plus the constant of integration, but, right? So I want to make sure you're comfortable with this. This is where students sometimes have a little difficulty. Let's make sure you're comfortable. Hunu, how do you feel? Good, good. All right. All right, well now what we do is at this stage now, we're going to put in the 2 for the, hold on here, for the x, right? We're going to the 2 for the x. So there's the 2, and there's and the 1. And now at this stage, it's a calculus 1 problem or a calculus 2 problem. Okay, so I'm not going to say a whole lot of words because I think you've done a lot of integrals. You know your antiderivatives, but please let me know if you have any questions. All right. May I move to the next page so we can finish this problem off? Just give me a few thumbs up and then we'll move forward. Okay, good. Ellie, Charles, Malik, wonderful. Okay. Juliana. Okay, so we continue. Of course, we're going to substitute in. We're going to substitute in the pi and the 0, which I do here, and we end up getting 0. Okay. In other words, this integral, which was the original, this double integral, which was our original double integral, and it was the volume between the surface y given by y times the sine of xy and the xy plane. That volume is equal to 0. So what do you think happened here? How could we have a volume of 0? Okay, Ian says either the surface is flat or it or it goes up and down, and it would because of the sine wave. So I'll show you the figure here in the book of that surface. One moment. It's really an amazing it's just amazing material. It really is. Okay, let me show you here. So we're going to figure 4 from example. This was example 3 in section 12.2. All right, so let me go ahead. Are there any questions on the computation here? Okay. Let me see here. One moment. Let me bring up the ebook. Okay, there's the surface, y times the sine of xy. Z equals y times the sine of xy. You can see the y limits go from 0 to 3. Well, the y limits go from 0 to pi in our problem, but they're drawing, it's like 0 to pi, but you see there's 0 to 3, but it's a little further than 3. And then the x limits go from 1 to 2. And you see how that surface, basically it's symmetric, and half the time it's above the xy plane and half the time it's below the xy plane. So, well, I want to be careful about saying symmetric, but what I'm saying is you can see that there's positive volume and negative volume, and it turns out that the net for this region of integration that we're using, it turns out the net total of volume is 0. How many think that's absolutely fascinating? I mean, it doesn't happen often, How many think that's pretty cool? Okay, Marwin's liking it, Ian's liking it. Good, good. All right, I'm going to ask you a question here. I'm going to go to the whiteboard. And I'm going to ask you a question. It's a which is better question. It's kind of like, well, I don't know if it's a great analogy. It's so bad I won't make the analogy. But let me just see here. So in this problem, this is our double integral. Okay. And the region R has x values that go from 0 to 1 and y values that go to 0 to 1. Okay. So now I'm going to ask which is better below. Okay. Which is better below. I'm going to write down 2 integrals. Here's integral 1. That'll be dy dx. And then integral 2 will be dx dy. Okay. And I'm wondering which integral below, let me spell that good, I can spell that well. Which integral is better below? The 1 or the 2? And maybe just to kind of help you, I'll put in the iteration grouping symbols. So when I say which is better, I mean in the sense which one can we find, which one can we find an answer to? Both double integrals represent the same number, but one of the double integrals, you know, the inner integral, is possible to do. The other one might be very difficult. And I'm wondering which should we integrate with respect to? Should we integrate with respect to y first, or should we integrate with respect to x first? Charles is saying he thinks y is better. Let's see what other people think. Any other thoughts? Okay, Ellie thinks maybe x is better. So I like it when, you know, smart people maybe differ on their how they feel. We'll have to, and this is new. Well, let's see. What would well, hold that thought, Ellie. What would the antiderivative be if we were to integrate with respect to y first? Now I saw Ellie bring in a log. Let me think here. Would would this here be the right antiderivative? I mean, if we differentiate with respect to y, the log of 1 plus x times y, what do we get? We're going to get 1 over 1 plus x times y times the derivative of the inner function, right? We're using the chain rule here. What's the derivative of 1 plus x times y, or the partial derivative of 1 plus x times y with respect to y? X, that's right. Oh, look, it checks out. This checks out. Here, though, so Charles, good instincts. Here, I'm not sure what the antiderivative of that would be with respect to x. We might have to divide x by, we might have to rewrite it. Maybe divide x by, no, hold on. Take like x here and divide it by 1 plus x times y. Maybe we could rewrite it. Does anybody want to do that, really? What do you think, Ellie? Are you more leaning now more towards integrating with respect to y first? What's your thinking? How would you? Well, okay. I'll tell you what. All right, I'll tell you what. I'll finish this up. Let's go ahead. I see your question here. Let's go ahead and finish this problem. So let's say that the answer is 1. Okay, and Charles is making a statement there. Let me work it out here. So integral from 0 to 1. Okay, this is what we got here. Now let me go down here. Okay, so this will equal the integral from 0 to 1 of and I know what I want to do. I'm just trying to get my crazy pen to work here. I'll have to do it with the mouse. Okay, the log of 1 plus x times 1 minus the log of 1 plus x times 0 close the bracket dx. This here, though, is just 1, and so no problem. Well, that's no problem, Charles. That's why we're doing this. And then this is just going to be the log of 1 is 0. So we're going to end up getting the integral of 0 to 1 of the log of 1 plus x. You can solve that doing what is it called? You can use integration by parts. you can use integration by parts. It'll take a while to do. So I want to try to, okay, no problem, no problem. You would let u equal, the log of 1 plus x, and you'd let dv equal dx. And, and there is some work involved, okay, but it does work. It does work. It will work out. Now, let me just see here. The second way would work, though. I like the first way better because it's a little more obvious to me. But in the second way, you could make a substitution. You could, if you were to integrate with respect, well, hold that thought. No. Second way would not work well. The first way would work, and we're doing it fine. Are there any questions on this? Okay, let me go ahead and stop the recording here. Okay, and I want to